In programming, it's often true that we can't see the forest for the trees. We may look at individual lines of code in a program and think, hey, that looks easy, but fail to really see how the entire program is working. Or we might dive right into writing our own program and get so caught up in the details that we can't keep that bigger picture in mind. Either way, there's a big difference between looking at code line by line and seeing how those individual statements work, versus seeing how all the details come together to make a complete piece of software. So in this lecture, I want to pull back a little bit and take a look at some of the bigger picture aspects of the programming process. I'm going to explain what's really involved in creating programs, especially as our programs get larger and more complex. This takes us into software analysis and development, what's also called software engineering. All of this is a critical aspect of computer science as a whole. We're going to spend the entire time in this lecture focused on just one program and the process of actually putting it together. I want us to focus directly on what it's actually like to develop a program. Along the way, we'll talk about 3 general principles that are important in practical programming. 1, plan ahead. 2, keep on testing. And 3, develop iteratively, in what I like to call a pyramid style. To see all of this in action, we're going to create a program to help you save money toward a goal. Maybe a new appliance, maybe a vacation, or a car, or a house, or a second house. Then, let's assume that you have a certain amount of money that you can set aside each week or month. You'll want a program that can help you understand exactly how many times you'll need to set that money aside in order to save up enough money to reach your goal. Well, mathematically, this is really simple, basically just a division. Now, I have deliberately picked a very simple example so that we can focus on fundamental challenges and pitfalls involved whenever we turn ideas into working code. Let's go ahead and start programming. It can be really tempting, and I mean really tempting, to just jump in and start writing code. But like many things in life, you'll often be better served by thinking about what you're going to do before doing it. So, the first thing that we should do when we start programming is not actually write code. The first thing to do is to stop and think about our program. If you were wanting to build a house, the first thing you'd do would not be to start mixing concrete. You'd first want to sit down and make sure you had the design plans worked out and could afford what you intended to build. When it comes to coding, an ounce of preventive planning is worth a pound of cure. So in this program, what is it that we really want to do? Well, we realized earlier that we needed division to calculate the number of payments. But in order for the program to do that, we first need to get information from the user about how much they want to save, and about how much they're setting aside each period of time. And what else? Well, we need to be able to present the results to the user. And that's probably enough to start with for now. Again, this is a simple example, but notice, in addition to the division operation, we identified 2 additional steps, one for input and one for output, that our program will have to do in order to work. And as programs get more complex, the value of planning ahead becomes more and more important. When professionals develop software, they'll often spend days or weeks or sometimes even months thinking about and planning their code before actually writing it. There are a wide variety of ways that people can actually do this planning, and the process has changed a lot over time. Quite a ways back, people would often use flowcharts to describe plans for code, and they're sometimes still used today. But nowadays, there are a much wider variety of approaches used in software design, with the outcome being design documents, UML diagrams, etc. Now, I don't want to focus on any one particular way of doing this planning. What's far more important than any specific tool is that before you sit down and start typing out code, you first think about and plan out your approach. Now, for our little program, we've already got a brief outline of what we want to do, those 3 main steps. For a problem of this size, that's plenty of planning, so we're just going to go ahead and start coding this up. Generally, you can stop planning at the point when it's obvious how to turn your plans into code. Now, it can be a good idea to start by writing comments to ensure that we know what needs to be done in each part of the program that we'll write. In this case, we can take our 3 main steps and write a comment for each of the main steps. Get information from the user, calculate the number of payments, and present information to the user. We'll next fill in the actual code for each of these steps. We'll start at the beginning, requesting and reading in some data from the user. We need two pieces of data from each user, the amount to save for and the amount that they're regularly going to set aside each period of time. For this simple version of the program, we won't ask for how long each period of time will be. Instead, we'll just calculate a total number of payments. So, we'll need to ask the user for two pieces of information, and then store each of those in a variable. Let's use the variable balance to store the total balance, and the variable payment to store the amount set aside each period. Okay, so we should have code that will read in pieces of information. What's the next thing that we should do? If you answered something like, do the division to calculate the number of payments, that's actually not quite right. Don't just focus on the code itself, keep your eye on the overall process for developing the code. The next thing we should do is test the code that we wrote to make sure that it works. Regular testing is so important in software development, and it's only by testing along the way that you're likely to catch errors that may otherwise slip through. Let me tell you a story. In December of 1998, NASA launched the Mars Climate Orbiter. Its mission was to travel to Mars, where it would go into orbit around Mars, observe its climate, and communicate that information back to us on Earth. The total cost of the mission was over $500 million. After about a 9-month trip through space, the orbiter finally made it to Mars. But instead of going into orbit and performing its job, contact with the orbiter was suddenly lost, and it would never be recovered. Now, from what we can tell, it burned up in the atmosphere of Mars. The mission was a catastrophic failure, and we never got the vital data that the orbiter was supposed to collect. Well, with such a devastating loss at a cost of $500 million, NASA was very interested in determining what caused the problem. Their investigation managed to determine exactly what the problem was, which is pretty amazing when you think about it. It turned out that there was one piece of software that was writing data using English units, pounds, while the software on the orbiter itself was expecting data to be measured in metric units, newtons. This error had been occurring throughout the trip, but in the way they'd set up the equations, the differences between pounds and newtons were small enough that the differences went completely unnoticed, until that critical point when the orbiter was ready to go into orbit and the whole mission went kaput. Now, spaceflight might be the most challenging task that humans have ever faced, so it's not surprising that there will be errors along the way. And you could blame this error on several different things, ranging from communication problems to process planning. But the end result is that a very, very small problem in a piece of software was at least partially responsible for the loss of hundreds of millions of dollars of work. And that leads me back to the importance of regular testing. After all, everyone encounters bugs in their code, not just new or bad programmers. Even the world's greatest programmers will have bugs in their code. Bugs occur when we make small mistakes, maybe in typing something wrong, or maybe in thinking about something wrong, or maybe in just not realizing all the consequences of some piece of code. When we write code, we never think we have a bug. We think it's all working correctly. The only way we're ever going to find these bugs is to run tests that help us know that they're there. Now, it's tough to blame the NASA programmers for not catching the bug that led to the Mars Climate Orbiter loss. Like I said, this is a really complicated problem. I'm sure they had many tests of various parts of their software. But the fact is, if there had been tests for the exact way that data ended up being created and used, they probably would have caught this problem, and then avoided the disaster that occurred. Now, I remember one specific bug in some code I wrote that one of my students spent weeks trying to deal with. I thought I had tested that code thoroughly, and in fact I had done a lot of testing on it. But I had still somehow missed testing one whole section of code. And as a result, the student spent weeks trying to find and fix the problem. But it showed how thorough testing, as code is being written, can actually save lots of time later on. Now, there's some people who will say you should test after every line of code that's written. After all, every time you write a line of code, you've potentially introduced an error. And more tests over a wider range of situations are never going to make a program less reliable. Now, realistically, line-by-line testing is a little too extreme, but it makes a good point. You can almost never have too much testing. My rule of thumb is test each logical section of your code. We should never write large amounts of code without stopping to check to make sure that it works. Here, we've written a grand total of just 2 lines, but it's still a good point to test. We've written the first logical section of our code. We want to see if we really did write code that will read in the values that we wanted and store them correctly. One of the simplest ways we can test code is to run it and print out the values of variables. So, we'll type in a print statement like you see here, and run our code. Now, when we run the code and enter a couple of values for balance and payment, like 110, we do get the values printed back out. So, all of this looks pretty good so far. It looks like the code we've written is working. Now, I should note that it can be kind of frustrating to have to stop the fun work of writing new code just to perform tests on something you expect to be working already. However, it's important to remember that the more code you write from the point you introduced a bug, the more trouble it'll be to find and fix the bug later on. And sometimes it will be too late to fix it all, like in the case of the Mars orbiter. So remember, your life will be easier, your code will be better, and ultimately more fun if you're in the habit of testing more frequently. So let's write and test our next section of code, the calculation. To determine how many payments we'll need to save up for our goal, we'll just divide the balance by the payment. Let's store that in a variable num remaining payments. To test this, we'll want to print out that variable to make sure that we got the right answer. And that happens to be the last of our 3 tasks, presenting the information to the user. So, we've actually got a program, and we need to go ahead and test it. So, let's run the code and say we're wanting to save $100, and we can save $10 a week. Oh no, what happened? We've got some error here. And if we read it, it says that there's an error in line 9 and that name balance is not defined. Huh? Oh wait, I see, I just mistyped balance. I accidentally left out the N. Okay, that's easy to fix. Okay, so let's try running that again. If we run it, we type in 110 and another error. What's wrong with this stupid computer? Okay, let's see what the error says. It says line 9. That's the same one we just fixed. So why is it giving me another error for something I just fixed? Okay, I guess we better see the specifics. It says unsupported operand types for / str and str. Now, that might not be very comprehensible to you at first, but what this means is that we tried to do a division, that's the / operand, between 2 strings. That's what the str means. So, the computer thinks that we're trying to divide a string by a string, which doesn't make sense. There's no such thing as division between 2 strings. Okay, our division is between the variables balance and payment. So that must mean that the computer thinks that both balance and payment are strings. Oh, I know, I forgot to convert them when I first read them in. I even missed it when I ran my first test to see if those lines were working. Okay, this should be an easy fix. I'll just add float around each of the input lines to make sure we're getting floats rather than strings. Remember, our input is coming in as strings, so we need to convert it to ints or floats if we want numbers. Okay, so I'm reading in variables as floats now, and then I'm calculating the division. So that looks better. Let's try this again. If we run, type in 110, and hey, it's working. I got the right answer. So maybe I'm done? Of course I'm not done. Just because this passed one test doesn't mean that it's actually doing what I want it to. Testing means testing lots of cases. So we have to try to run a few more tests. Okay, if I enter 325 and 60, we get an answer that looks right, even if it's got a lot of decimal places and truncates at the last decimal place. Good so far. Let's try another test. Oh, I know. Let's try entering a payment of 0 and see what happens. Another error, this time a division by 0. And that kind of makes sense. If we're not setting aside any money, we'll never save up any. But having the program give us an error and crash doesn't seem so great. So let's think about what we can do to fix that. The problem comes up when we're trying to divide by 0. So basically, we want to make sure that the user enters a payment amount that's not 0. This program is assuming that we set the same amount aside each time, so we have to have a positive amount or it won't work. How do we perform a check? A conditional statement, an if-then statement. So let's put something in the code right after we read in the payment to make sure it's not 0. We'll have an if-then statement, and the condition seems obvious. We want to check whether the payment is equal to 0. But what should we do if it is 0? Well, there's a few options. Maybe we want to ask the user to put in a new value. Or maybe we want to say, that's no good, you can't reach your goal if you set no money aside, and just close the program. Or maybe we want to say, 0 is never going to let you save enough money. How about if we use some small value like 1? We need to think about what ounce of prevention functionality we really want to include if someone enters bad information, especially bad information that could crash our program. Let's say that we go with the first option for now. So, we'll write an if statement. For the condition, we check whether the payment is equal to 0. Notice that we need the double equal sign. Then, if the condition payment is equal to 0 is true, we'll print out a message to the user saying, you need to save something, so please enter a non-zero value. Notice that in this case, we're getting another input, so we can enter something new. Okay, let's run this to test it. If we enter 100 and 0, now we get the message, and we get a chance to enter some other value like 10. That's a whole lot better than what we had before. Okay, what if we run it again, and despite the warning, the user decides to enter 0 again? Well, in that case, things still fail. There's a way we can keep asking the user for a value until we get one that's good, and when we learn about loops, we'll see how to do this. But for now, we'll just hope that this is enough to handle our problems. We've given the user a warning, so hopefully the user will read the directions. Let's do another test. Let's try entering 0 for the balance. Well, that one seems to work okay. It says we need no payments, which makes sense. Let's try one more test. Okay, it seems like regular values are working okay. We can handle the cases where we enter 0. What if we enter a negative number, like a payment of -10? It looks like we get a negative answer. The math is correct here, but it doesn't make a lot of sense. We don't need to be talking about saving up negative amounts, and saving up negative dollars will never get us to our value. So we probably ought to put in another check just to make sure that we handle the negative cases correctly. For the balance, if the user enters a negative number, there could be several reasons. Maybe it's an error on their part, or maybe it means there's already enough money saved. The amount they need is less than 0. We'll assume that it's the second case here, and so we want to treat the balance as 0, so that we compute that no more payments are needed. So in this case, we'll write a statement telling the user what we're doing, and just set the balance to 0. Okay, how about handling negative payments? We've already got a check, so let's just modify the check we had previously to also handle negative cases. We need to adjust the condition, so we're excluding payments less than or equal to 0. And we need to adjust the message to say that they need a positive number. Okay, so let's test our new code. So, if we enter a negative payment, we get the message to enter a positive value, and it seems to work. Now, if we run it again, and we enter a negative savings goal, we get the message, but then we also get asked for a payment again. That doesn't make a whole lot of sense. We don't need to save anything, so why make a payment? So, let's turn that first statement into an if-then-else statement, and do the whole bit about asking for payment info only if needed. That means we need to put in an else, and also to indent all the payment part. And there's one more thing. Since we're still computing balance divided by payment, we need to set some payment value if we're going to have a negative balance, so we'll just set it to 1. Okay, now if we run this, and we enter a negative balance, it goes right to the end. Great. And if we run this again, with reasonable values, we still get the right messages when we have a positive balance. So it doesn't seem like we broke anything. Everything seems to be working. Now, you might look at this program and see additional areas that could be improved. What improvements would you make first? Well, here are some I see. The program could interact more with the user. Maybe we want to ask for the user's name and use that in the output, or ask what they're saving for and use that. Maybe we want to compute the number of payments differently so that we round up to the next highest integer. We could make all sorts of further modifications to the program to improve it. This does bring up the other big idea that I want you to learn from this lecture, and it's one you've probably already seen in practice. It's called iterative development. When we make improvements, we're often adding additional features onto already working code. The process is called iterative since it consists of a series of iterations, each one adding a little bit more to the previous round. But the key is that we don't move on to the next iteration until the previous one is working. In our program example here, we didn't move on to trying to handle the trickier cases with negative numbers and 0 until we first made sure that the basic cases were working. Let me give you one of my favorite analogies for building software. Two very different but very strong architectural structures are arches and pyramids. When software development goes well, the whole process is like building a pyramid. First, you lay out a base of stones. Then you add a second layer of stones. Then another layer on top of that, and so on. With the pyramid, you add and adjust each new layer one by one, getting stones into a stable position before moving on to a new layer. At any given point, the structure you've already built is very stable. You could stop partway through and you would still have a solid, stable structure. Now, in terms of code development, we want to build code using a pyramid style whenever we can. That is, we want to build up new code on top of other code that we know is working. Each iteration, we can add one more layer to the pyramid, building a new, stable layer on top of an existing stable structure. Now, unfortunately, many times people will develop code like they're building an arch. An arch only holds its shape if every brick in the arch is there. So these programmers will write lots of code, and finally they reach that one glorious moment when they've written the last line of code that they think they need, and then they run the code, and they find that the whole thing fails. There was some piece missing along the way, or that wasn't working, and as a result, the entire program has problems. Unfortunately, there's no solid base to go back to, and so they have no definite idea where to look for the problem. They may have to start all over. So, you always want to make sure that the code you have is stable, working code, before you try to add on something else. Repeated testing will help ensure that you always have a stable base where you can return, without needing to re-examine everything. Now let's try making some improvements to the code we have. We have a solid, stable base to work from, so let's build, pyramid style, on top of our previous code to create a more complex program. Let's say that we'd like to have a friendlier interface. For instance, let's say that we want to print a message about what the program is for, and get the user's name and what's being saved for, and use that information in our messages. How might you modify the program to do this? Well, here's one solution. It's not the only one, though. Notice that we start out by printing a message saying that the program is to help you determine how long you'll need to save. We then ask the user to enter their name and what they're saving for. Next, when we ask for the balance, we can actually include the user's name and the name of the item. It makes the message a little bit friendlier. Again, at the very end, when we print out the message about how many payments are needed, we can put the name of the item in there. So, if we test this out and run it, I can enter my name, and then I'm saving for a car. Notice that the message directly asks, "Okay, John, what is the cost of the car?" And after I enter the cost and the payment amount, I'll get another personalized message at the end. Again, we now have a stable system. We could choose to add something else onto it at this point. Let's say that we wanted to handle the case where a user entered a negative payment a second time, even after a warning. how would you write some code that would detect that that had happened and do something different, like set the payment value to 1? Here's one way to do that. We can add a nested if statement. We'll check again to see if the new value entered is again negative. If so, we'll scold the user a little and tell them that we're going to just assume the payment is 1 and set the value accordingly. For the sake of time, I'll skip testing this right now, but that would be the next thing to do. Okay, so once we've tested and reached a new stable state, we can do another iteration and improve it again. Let's say that we wanted to make sure the number of payments is always an integer, rounding up if needed. The number of payments is a floating point number. If we convert a floating point number to an integer, it will remove the fractional part and just give us the whole portion. So, one option would be to convert the number of payments to an integer and add 1 if we had to drop a fraction. Can you figure out what the code would look like to do that? Again, here's one possible solution. It's not the only one. We convert num remaining payments to an integer, and we see if it's actually smaller than the floating point number. If so, that means that there was some fractional part that was lost. If so, we add 1. So now, if we run this program, and I say I want a ticket that costs $100, and I'm saving $75 a pop, the program will tell me I need to make 2 payments to get the ticket. Or, if I'd entered $25 in savings, I'd be told 4 payments would be needed. So, the program seems to be working for both the case where I need to round up and the one where I don't. At this point, we've added several layers of improvement on our program, making sure that we reached a stable state after each one. We already have a much more complex program overall. If you tried to write this program all at once, no telling how many errors you might have had along the way, and how much trouble you'd have had fixing it. So, there are 3 big takeaways from this lesson. First, as you develop code, it helps to plan ahead for what you're going to do before you actually write the code. Second, the more testing, the better. Everyone, and I mean everyone, is going to make mistakes when they code, and you're only going to find these by testing your code. And finally, you want to make sure that you're building your code incrementally, pyramid style, not arch style, so that you always have a working base to go back to. As we look at code in later lectures, we won't usually take the time to show the development process quite to this level, to show each line being typed and testing each section. You'll mostly see me presenting a bunch of code that looks clean and runs correctly. But I want you to remember that the actual process of development is very different from seeing a bunch of finished code that looks clean and runs correctly. Clean code is always the result of many repeated runs and tests. You're going to make mistakes, deal with bugs and errors, and have to test your code repeatedly. This is a totally normal and unavoidable part of writing code. Everyone encounters these challenges. The secret to handling these challenges is to start with an ounce of planning, test until you have a stable base of code, and then iterate through the code to make additional improvements. If you stick with this approach, you'll be able to make the computer do some incredible stuff, and feel great that you were able to organize things so precisely.